All right, let's continue our discussion on weather theory and specifically continue our discussion on atmospheric stability. Everything up to this point we've covered has to do with how the cycle of weather patterns and weather events are started with the heating and the cooling of the Earth's surface, along with the weather pattern flows and the Coriolis force, which has an impact on pressure systems, low pressure systems and high pressure systems in the atmosphere. And those pressure systems are accountable for where air travels, how it travels, the speed at which it travels. And we're going to dive more into atmospheric stability because that's really, once we've got the picture figured out on where the air is traveling and how the pressure systems are working, atmospheric stability determines what type of weather we're going to see in any given location. So again, just to kind of revisit some definitions, stability of the atmosphere is the resistance of the atmosphere to allow vertical motion of an air mass. And we talked last time about how that is related to the temperature of the atmosphere as you go up in altitude. An unstable air mass is caused by temperature decrease higher than standard lapse rate. And so we talked last time about a 2° centigrade per 1,000-foot lapse rate. So that'd be a decrease of 2 degrees as you go up every 1,000 feet. And that is indicative of a stable atmosphere. Anything more than that, 3-4 degrees per 1,000 feet, would be indicative of an unstable atmosphere where you might see what we call convective activity, convective currents, turbulence, wind shear, potentially thunderstorms if there's the correct ingredients for a thunderstorm. And so I want to take a minute to also provide a definition or an equation rather called the universal gas equation. And it is right there on the screen. PV equals rho RT. And P is pressure, and this equation is universal for any gas, but of course we're talking about air. And if you're given a specific area or volume of air, this equation holds true. So P is pressure, V is volume, and that side of the equation must be equal to the Greek letter rho, which is that short-looking P. That is air density, or density. R is a constant depending on which gas you're talking about, and then T is temperature. So this equation simply states that your pressure multiplied by your volume must be equal to your density multiplied by a constant multiplied by temperature. And so the reason I bring this equation up is because it has a significant impact on all of our weather theory and the science behind why things happen in the atmosphere. I have an example there at the bottom of the screen which will help us in our future discussions. With regard to density, you can see the first bullet point there. A low moisture air mass, so in other words a volume of air that has a low moisture content, is characterized by high density. So that air pocket, that volume of air has a high density, and that means that the air molecules are very tightly packed amongst each other, very dense, and this dense air mass sinks because it's dense. Think of throwing a brick into a swimming pool. That would be a great example. The brick is going to sink to the bottom. And in this scenario of dense air, the atmosphere is stable. On the other hand, a high moisture air mass, where you've got a volume of air that also has pockets of moisture molecules in it, that particular air mass is not going to be as tightly packed together. Think about a volume of air that also has a lot of water moisture in it, the air molecules, just by definition, will not be able to have a tightly packed configuration. And so the air density for that specific situation would be lower because it's having to share a lot of that volume with the moisture. And thus, that specific air pocket with a lower density is going to rise compared to a pocket of air that may not have that much moisture in it. We've already talked about earlier, pockets of rising air are characteristically less stable. Remember when we discussed that with our temperatures, the more you have a pocket of air rising, the less stable it's going to be, the more convective it will be. We use a term there, convective. And so just a few more notes here to kind of close up our thoughts on stability, and as we move more and more towards discussions on weather events that occur due to moisture, due to instability, things of that nature. Really, when it comes down to looking at the resultant weather pattern in a specific area, the combination of moisture and temperature determine the overall stability of that specific air pocket or air location. We talked about temperature more in the last lesson, where the faster you have a temperature drop in a given altitude range, the less stable that air mass will be. And we just discussed in the last slide how the more moisture you have in a pocket of air, the less dense it is, therefore the more susceptible that air pocket is to rising. So kind of in conclusion, if you've got cool, dry air, think of the beach setting on some California coast somewhere where you have extremely low humidity, very dry air, nice and cool, maybe 60s or 70s degree Fahrenheit. That's a very stable air mass. That's a very stable weather situation. That air mass is resisting vertical movement, and therefore you're not going to see a significant amount of, I'd say, convective turbulence, thunderstorms, any sort of weather pattern there. On the other hand, if you have warm, moist air, that is indicative of an unstable atmosphere that promotes vertical development or convective air movements. Think of Dallas, Texas in the summertime when you have moisture in the air and you have heating, the very hot temperatures in the summer, and those hot temperatures at the surface cause the surface air to rise. With the moisture in the air, that also creates a low air density situation, so that air is more susceptible to rise, and you have thunderstorm development. So two different scenarios there: cool, dry air, very stable; warm, moist air, very unstable. And like we mentioned in the last lesson, the temperature inversion situation can also further stabilize your atmosphere. So if you have cool, dry air, and as you move up in the atmosphere, the temperature increases due to a temperature inversion, which, as we've discussed before, is not normal. It's an inverted situation. That's going to further resist the vertical movement of air in the atmosphere, which will keep that air mass even more stable. So hopefully we're starting to see a theme here with the resultant air mass temperature and air mass moisture content. Now, the moisture content affecting the density or the buoyancy of the air mass, and how those two variables can really affect the rate at which air moves in a vertical manner in the atmosphere. So that will have high impact on what that weather pattern will look like. Just one more graphic. We just want to hammer home the point that moisture having an impact on air density. Again, I really just, let's think of the swimming pool example. If you've got a, brick, and let's pretend like the brick is a pocket of air. Well, the brick is extremely dense compared to the swimming pool, right? And if you throw the brick in the swimming pool, it will sink to the bottom. The brick has no space in its molecular structure to fit any moisture or any other lighter materials, so it's going to sink straight to the bottom. If you take a sponge, which would be a characteristic of a material that is not as dense as its surrounding environment of the swimming pool, if you throw that sponge in the deep end, that sponge is going to float for a period of time. And so it's just another example of how, think of an air pocket. If it's super dense, meaning it doesn't have a lot of moisture content in it, it's going to stay where it's at, it's going to sink, it's going to promote a stable atmosphere. If you have a pocket of air that has a lot of moisture on it, or moisture in it, the opposite will occur. That moisture is going to cause that pocket of air to be less dense than the surrounding air, and that air pocket is going to rise. So definitely want to, make sure we understand how the moisture content and the temperature of the atmosphere, the temperature profile of the atmosphere can have an effect on atmospheric stability. A couple of definitions here on the screen. So moisture content is measured in terms of relative humidity. So if you have 100% relative humidity, it doesn't necessarily mean that a pocket of air is 100% moisture. It means that that pocket of air has reached its maximum moisture content. And obviously, if any sort of moisture is attempted to add to that pocket of air, if you try to introduce more moisture and it's already completely saturated, that pocket of air will reach its dew point temperature. And this is the point at which the air pocket or the atmosphere cannot hold any more moisture, and you'll have a moisture event that might be dew on a surface outside, it might be frost if it's below freezing, and it might be rain, snow, frozen rain, things of that nature. So once a pocket of air has reached a point when it can hold no more moisture, it reaches its dew point, and what we call a dew point event occurs, whether that be rain or dew, things of that nature. Want to spend just the next few minutes talking about fronts, weather fronts. So kind of just looking over the past couple topics we've touched on. Obviously, we touched on the big picture, what causes air currents and low and high pressure systems to exist. We've touched on stability of the atmosphere and the relative stability of certain air masses, things of that nature. The next thing to touch on that will help us further put the total weather picture together is what we call weather fronts, and kind of a similar terminology of weather systems. So weather fronts happen to be really just the frontal boundary of an air mass. And as you can see from our prior discussions in the lesson, based on the heating and cooling of the Earth's surface and the rising and the falling of air masses and the movement of winds and things of that nature, the atmosphere is going to take on the characteristics of certain atmospheric conditions, certain Earth features, things of that nature, and these these masses of air are going to form across different regions of Earth. And those air masses are indicated on your weather charts by the frontal boundaries. So when you're looking at the evening news, let's actually pull up one of the maps here. you're looking at like the weather map online or watching the evening news, and you see some of these frontal boundaries on your weather map, like for example the blue jagged line or the red flagged line, those indicate the frontal boundary of warm and cold air masses as they move across the country. Of course, those masses are moving across the country based on the flow of the Earth's atmosphere and things of that nature, things that we've discussed prior. It's important as an aviator to understand what each of these air masses bring with them characteristically as it pertains to weather. Because as you're looking at your weather chart, you're going to see these air masses and these fronts, and the first thing that you're going to have to determine is the safety of flight and what type of weather you're going to see as you fly through these different air masses. I'm going to touch on each type of them here briefly, and then kind of walk through what type of weather you see. Again, the fundamentals that we've gone through as far as the rising and the falling of air masses and the temperature changes and convective activity and atmospheric stability, these all come into play in each of these different scenarios, whether it's a warm air mass or a cold air mass coming through a certain region. But what you'll find is a lot of the weather phenomenon that occur as different air masses come in contact with each other. So, for example, let's start with a warm front. And you can see these on your weather map, but as a warm air mass advances and comes in contact with a cold air mass, and you can see the picture on the screen, this is in general what the cross section will look like. They kind of call it a wedge as the warm air mass advances on the cold air mass. You can see what can occur and what the characteristics are. Warm fronts, based on their characteristically lower density, have a higher moisture content. And so there's a lot of moisture a lot of times in warmer air. We've talked about that. As that warm air approaches and comes in contact with the cooler air, a lot of that warmer air will actually reach its dew point, like we talked about before, and the air will no longer be able to hold the moisture content that is in it. So the excess moisture will condense and form clouds and rain. And so what you can expect as you fly into areas of warm air mass coming from maybe a cold air mass to a warm air mass, you can expect poor visibility, nimbus clouds, so clouds producing rain or having high moisture content. And of course, if the temperature is right, you'll have snow or freezing rain. But yeah, using kind of the theory we learned before about warmer air having a higher moisture content, and then that air being introduced to colder air, which reduces its temperature to the dew point, you're going to have moisture squeezed out of the air, so to speak. It's going to condense, just like maybe a cold drink condenses on a hot summer day, and the moisture will form out of the air as a cloud or rain if there's enough of it. Cold front, so flying from a warmer air mass to a cooler air mass. Similar theory pertains, but usually the characteristic, I would say, replacement of air mass, cold to warm, is a little bit more active, a little bit more convective potentially. Imagine yourself sitting in your driveway on a cold day in the middle of a cold air mass. Warm day, warm air mass. So it's a hot summer day, and a cold air mass comes in and takes over your warm air mass. Well, that cold air mass, which the opposite of warm air. So cold air is going to be sinking, it's going to be low, because warm air wants to rise, cool air does not. The cold air is going to come in and wedge in your warm air and cause the warm air to rise, which it wants to do anyway. So it's already predispositioned. So your warm air is going to be replaced with cooler air. And remember, we talked about before, your warm air typically has a higher moisture content. As that warm air rises, which it does so potentially aggressively, and what I mean by that is potentially convectively, depending on the stability of your atmosphere, that moisture content in your warm air as it ascends is going to condense, just like it did with the warm front example. But due to a potential more aggressive, I would say, takeover of cold air mass to a warm air mass, which is typical, it could create atmospheric stability problems, which we can relate back to a decreasing temperature with altitude and high moisture content. So we're back to our example of warm air, which is less dense, which has a higher moisture content from the prior slides, and that warm air is being forced up by a cold air mass, potentially in an aggressive manner. And what this is going to cause is not necessarily your gray, rainy day. This is going to cause potentially convective activity, thunderstorms, clouds, real white puffy cumulus clouds with extensive vertical development. And this is what is very, very characteristic of a cold front air mass coming in to take over a warm air mass. Happens all the time in Texas in the spring. And finally, we have occluded fronts. So occluded fronts are kind of a combination of cold and not as cold fronts approaching and making contact with each other. It's not, what I would say is the best way to define occluded fronts are when you have kind of a multitude of frontal boundaries coming together, whether it be really cold air with an air mass that's not as cold, but it's not necessarily warm, or maybe it's, like in the bottom example, maybe it's cold air coming to take over an air mass that's maybe colder, or maybe it's winter time up north and you have cool air coming to overtake like freezing cold air. Really, the bottom line for any frontal system, including these occluded fronts, is based on the moisture content of the air that is being collided with, and the stability of the atmosphere of the weather system that's coming in contact. You're going to have various types of weather situations. So when you're looking at any frontal system, whether it be cold or warm or a combination of the two, which is an occluded front, you just want to be cognizant that you're going to have a weather situation there, whether it be the vertical development of the atmosphere and potentially clouds, rain, snow and ice if the temperature dictates, things of that nature. So really the bottom line is the weather of any of these systems is determined by stability of the atmosphere, relative temperature change, and what type of moisture content the different air masses have when they come together. Couple of notes that will help during your written test or your flight test, some things the examiner may bring up. When you're flying through these frontal boundaries between air masses, you're going to see a temperature change, so that'll be very evident. You're going to see pressure changes, okay, and you're going to see a wind shift. So really one of the most popular questions an examiner might ask you is, hey, you're flying from an area, from a warm air mass to a cold air mass. So you just flew through a cold front. What's the biggest difference you're going to notice? And really the best answer for that is you're going to notice a temperature change, obviously, and you're going to notice a change in wind direction and speed. because the cold air mass just happens to have different weather pattern. It has a different atmospheric stability and probably has, different types of clouds, things of that nature. But the biggest, difference you'll see in the cabin of the airplane is the outside air temperature is going to go down and your wind is going to shift. Maybe you had a tailwind before and now you have a headwind, or maybe your wind was from the south and now it's from the north. So that's the biggest change you'll notice from the cabin. All right, in our next segment, we're going to talk about some of the weather phenomena taking place inside these different air masses, such as clouds and thunderstorms, rain, things of that nature.